Hi, good afternoon. This is really a chapter, the elasticity, and I will say stress and strain. And that one is actually related to materials. And just here, I will say, what if we have a mass that is, like attached to a wire or a cable? And then we're gonna see that because that cable is gonna be affected by the weight, pulled by the weight, then we're gonna say that Hooke's law is gonna be applied, where it's gonna be like the force and the change in the length are really directly proportional, and the proportionality constant is K. As we are increasing, or as let's say the applied force is doubling, the change in the length is gonna double. Now I will say if we keep increasing the mass, we will not, of course, still have like that elastic region valid. We will find that there is a limit where we're gonna have the elastic limit, and then therefore here I will say we will have a deformation happening to the cable, and we're gonna enter what is called a plastic region, and then finally we're gonna have a breaking point where that like cable is not gonna be able to bear up with the extra weights. Okay, like here, from here to here, we have this is the proportional limit where Hooke's law applies. The elastic region, it is where we're gonna have the curve is a straight line, and from the slope here, we're gonna get the value for K. And I will say after that, we're gonna enter a non-linear region. Okay, that is really here from the between the elastic limit. Is still the object will returns to its original length, but it's not linearly. Beyond this point, we are going to find that it does not return to its original length and the deformation is permanent. Okay, till it reach the breaking point where we are going to find that there is a maximum force that can be applied, just without breaking the thing. Okay, this is, we will reach what is called the ultimate strength of the material. Now, we are going to maybe talk more about quantities, and we will talk about something called Young's modulus. And here, in general, there is a quantity defined to be the stress and another quantity called strain. The stress is defined to be force per unit length, per unit area, sorry. And that it has units of newtons per square meters, and that is pascals. And the strain, it is measuring the deformation, and that deformation may be in the length, maybe in the area, and maybe it's in the volume. Okay, we can say that the stress is proportional to the strain, and they are connected by this constant of proportionality. Now, first, we are going to discuss here, I will say, deformation in length. Then I have a rod or anything that is going to be subject to a force. Either that force is going to be stretching like this, or compression is the same. Then we will say that this is F over A. It is the stress, and the strain, it is the change in the length divided by the original length of the thing. They are connected by a constant called Young's modulus. Okay, and I will say it is one of the elastic moduli, and why it is about length. It has different different values for different materials. For example, for iron cast, it is 110 to the 9, whereas it is 200 to the 9 newtons per square meter for steel. This is why we prefer to use steel. Look at this here, tension in piano wire, 1.6 meter long steel piano wire has a diameter of 0.2 centimeter. How great is the tension in the wire if it is stretches 0.25 when tightened? Then here, L0 is 1.60. R, it is 0.2 10 to the negative 3, 10 to the negative 2 meters divided by 2, because I want to change the unit into meter and also, convert into meters. I'm trying to find what is really the force of tension when it is stretched by 0.25 centimeters. Again, convert this because this was given in meters. Okay, of course, I can rearrange. This is F over A equals Y delta L over L0. Then I'm going to rearrange the values, and I will say Y, it is 210 to the 11 Newton per meter square. Now, the cross-sectional area, if we look at wires, they have a circular cross-sectional area. Therefore, the area, it is pi r squared, and that is going to be 980 for that. Now, also, we might have something called shear stress, and of course, shear, strain. Now, if I will apply forces parallel here, this is F and here F, and these are really parallel to the surfaces, like the scissors is one of the example on these. And then what is going to happen, I'm going to have a deformation in the, I will say, in the, what is called the area. And like here, if you look, okay, this one, I will say this point, it is on the same level at this point. Now we're going to have, there is a shift that is called delta L. Now that is, we call it the shear modulus. Volume change, it is called bulk modulus, and that is when we're going to have kind of, a force acting like this, and then we're going to have the change in the volume is with respect to the original volume is going to be minus 1 over B 0, and that is, we call it the bulk modulus, the change in the pressure. Now that negative here to tell you that if there is an increase in the volume, there is going to be a decrease in the pressure. This is again the same thing, changes in length, cross-sectional area here is going to be pi r squared. The stress, it is 4 per unit area, and it has units of a Newton per meter square. Now there will be a change in the length, and that is called the strain. The strain has no unit, and this is just explaining for you the same thing. Y equals stress over strain. Let's have that one here. This is the same example that I did. This is the same thing. I want to go to the other, okay, this one here. I have two examples. A 50 kilogram bucket of concrete is suspended from a steel wire that is 1 millimeter in diameter. Okay, this one is repeated. And 11.2 meter long. What distance will the wire stretch? Young's modulus for steel is 210 to the 11 pascals. Okay, the force that is acting on that bucket is going to be the weight of the bucket, which is mg, which is 50 kilograms times 9.8 meters per second square. Therefore, the weight, it is 490 Newton. Now, for the steel wire, we know that Y, it is 210 to the 9 pascals, or 210 to the 11 is going to be the same. 1 millimeter diameter, it is 0.5 millimeter radius, and that is 0.510 to the negative 3 meters. L0 here, it is 11.2, and it's very straightforward, like calculation. Force per unit area equals Y times delta L over L. I can rearrange the variables. Delta L is F over A, L over Y, and that is going to give us 0.035 meters, which is 3.5 centimeters. Another example here, it is about opposing shearing forces. When we're going to say opposing shearing forces, these are going to be parallel, are applied to the 3 by 4 centimeter faces of a metal block measuring 3 by 4 by 5. Then this is really the face that they are talking about, where the shear forces are acting. And I will say, by what distance does the block become slanted? Now it's gonna, like, the shape of it is gonna change based on the shear, I will say, deformation. The shear modulus for the metal is 8.10 10 to the 10 Newton per meter square. Here I did call that here. Okay, this is really the picture of it. I did call this is X and this one is H. Okay, to measure, like, it's like we did use in the previous delta L over L. I don't, maybe I'm not like really very comfortable with delta LL, because it is very similar to what we did with the changes in length. Okay, then here X is going to be F over A times H over S, which is the shear modulus that was given. And then this is 3,000 newtons. Area again here, it's gonna be length times width, then is going to be 4 10 to the negative 2 meters times 3 10 to the negative 2 meters, which is going to be, we can say it's 3 times 4 10 to the negative 4. And that number here, this is we said like the width is going to be 5 10 to the negative 2, and that is the value is going to be 1.54 10 to the negative 6 meters. Okay, this completes the whole chapter. Thank you.